Okay. If I look at this one right here, let's see here. If we look at the framework of it, just the way the carbons are laid out. Okay, they're kind of laid out like a cross there, right? And in this case, there's a branching point. And scrolling down here, they're all connected to one another in a linear fashion. Okay. If I were to redraw these using my lazy chemistry shorthand here, I get that. Oops, that was an ugly 3. Again with the ugly 3s. You know, you wouldn't think that I just spent the past school year teaching my 6-year-old how to make her numbers. There we go. That's better. Okay, can everybody see how they're the same? Okay, I could have drawn this. I'm not going to draw like a reaction arrow, but I could have drawn this and those two are the same. They only differ by virtue of the rotation of the carbon-carbon bond. All right. Now when we get down here, I can draw this structure, which again is wretched. But it gets the point across, I think. And if I look at the same connectivity here, okay, I get the same overall structure. Except if I were to really express what Brock-Norton was doing, I would have drawn it like this. Again, same structures related by the fact that there's an ability for the carbon-carbon bonds to rotate freely. Are there any questions about that? Okay, good. That just sounds like a fun test question, doesn't it? Like I gave you C10, H22, and said come up with all the isomers you can come up with. Are there any other ones that I missed? What is it? Just
3 carbons in a row, and then the middle carbon has 2 branching down off the bottom.
Say again? 3
straight line carbons, and then carbon 2, you've got 2 more carbons coming down off of it with 2 more methyl groups.
Okay, so if I'm understanding what you're saying,
Or methyl.
okay, you can tell me if I'm wrong here. Okay, you're proposing something like this, 3 carbons in a row. And then on the second carbon, what do we have?
And one, like on that second carbon,
Yeah.
there's another carbon coming off of that, and then another carbon coming off of that. CH2, CH3.
CH2, CH3? 1, 2, 3, 4, 5. That's all your carbons there, right?
I think so.
Have I expressed what you intended to express?
Because if you got CH, CH2, and then like the CH3, instead of doing a double on that, it comes straight down off that second one. So like,
Come on up and draw it for me. Don't you go erasing mine.
okay, I'll do my own. Mhm.
Okay, you can erase mine now.
Did I win? Yay!
Kinda, sorta. I'll show you why. I'll take care of it. All right, so I was not able to reproduce what you were expressing. Now, I want you to look at the structure very carefully. I want to redraw this. Well, I don't need to. You use my lazy chemistry shorthand, right? We have carbon and carbon branched from a single carbon to carbon to carbon. And if I yeah, right here. Okay. Now, if I were to draw this out differently, okay, I'm going to use my crazy organic chemistry shorthand now, even crazier. Okay, I'm going to say CH3 Do you agree that that is an equal representation of what you have drawn?
Except you don't have the single H and then the double H in those two.
Oh, there's two H's on this.
Yeah.
Right there.
Single, yeah, pretty much.
Okay. Now, what? There are 1, 2, 3, 4, 5 carbons. We're good. Yep.
Okay, so it's the same thing as that.
Right.
Okay.
These two are the same. Now, I know it's hard to see that, but basically you take this top molecule here and you flip it around.
Okay.
All right? But that is a very, very easy thing to confuse, especially when you're taking a test, right? So you got to be careful when you're doing these types of problems. All right. So we can now formally start our chapter on alkanes. Okay, and this is chapter 2 in your book. Okay. There are many types of alkanes that we have encountered in our everyday lives. Okay. For instance, the ones we've already gone through. What did I say this was called? Methane. Okay. Where does methane come from? It comes from the ground in the form of natural gas. We use it to heat our homes. We use it to cook our food, unless we have electric stoves and electric heat. From cows. One that we don't like to talk about so much, but there's probably been more money dumped, and I don't intend any puns, money dumped into the study of cow flatulence. And I'm serious. If you look in, you can actually look that term up, and you will find grants that have been made by the government. Because when you think about it, it poses a huge issue for agricultural systems. I mean, can you imagine having an entire barn full of cows and then having a match be lit? I mean, sometimes you'll actually see these types of facilities with pilot lights at the top of them. Anybody here live close to a landfill or ever driven past a landfill? You see those big tubes with flames coming out the top of them, right? Okay, what they're doing is they are taking the methane gas that's being produced by the anaerobic digestion of waste by bacteria, and it's setting it on fire so it doesn't explode underground. As a matter of fact, there have been accounts of people living close to landfills and that landfill gas kind of seeping its way down through the soil into somebody's basement through a crack in the basement and hits the pilot light on their furnace and their house goes poof. Okay, so what can we say about methane in terms of its properties?
Combustible.
Combustible. What else? Solid, liquid, or gas?
Gas. You can't really see it.
It depends upon what planet you're on. Okay, and I say that half tongue-in-cheek. On Earth, we see methane as a gas all the time, but there is such thing as liquid methane. As a matter of fact, that one of the gas giants in the outer atmosphere has oceans of methane. So it can be condensed into a liquid, but it would have to be very, very cold and under high pressure. Okay, so that's methane, and we know it's combustible. We know that we can find it in we can find it in landfills. We can find it in swamps as well. Again, because you have anaerobic digestion taking place in the swamps. As a matter of fact, that's how it was discovered. Anybody ever hear of something called a volt, an electron volt or voltage? Okay, that was named after Volta. Okay, and Volta was going along in a swamp in a boat, and he noticed some bubbles coming up, and he went and gathered up the gases, and that's how methane was discovered. Okay, ethane is also a constituent of natural gas. Propane less so. Oops. Where do we see propane usually?
Gas grills.
Okay, gas grills, right? Or on, anybody watch King of the Hill? All right, so you got that joke already. I won't do it again. Okay, if I have 4 carbons, what did I say that was called?
Butane.
Butane. Now, obviously, depending upon the structure of the compound, we assign a name to that compound. But my goodness, we can have more than 4, right? We can have 5, 6, 7, 8. If you look at the, may I borrow this for a second? I didn't even wait for an answer. Polyethylene, okay? This has tens of thousands of carbons in a row. Thank you. Okay, we have all these carbons that are lined up. That means that for every single one of these compounds between 1 carbon and 10,000 carbons, we have a different name, right? And I don't know about you folks, but by looking at the naming system that I put on the screen so far, I don't have very good hopes that we might be able to learn the rest of them, right? I mean, they're all kind of archaic looking. What does methane and CH4, where did they get this from? Well, it turns out that a lot of the early chemicals were given names by people who found them. You know, if I went out and I went to the swamp and I found, you know, CH4 and discovered it and figured out the structure and I gave it the name Doug's Chemical, I would call it Doug's Chemical. And all the people who worked with me would call it Doug's Chemical. And, you know, maybe I file a patent for it and it's Doug's Chemical. And then somewhere across the world, you have John. And John finds methane also, but he calls it John's Chemical. Now we have 2 different factions on opposite sides of the planet talking about the same chemical with 2 different names, and you have all these people reinventing the wheel. Okay. Unfortunately, some of those original, you know, names like John's compound have stuck. but at least some of them make slight sense. Actually, for me, one does. And that's the butane. And that's because butane has 4 carbons, just like 1, 2, 3, 4. This compound here, which is called butyric acid. Okay. Butyric acid also has 4 carbons, so that's well, okay, that makes sense. We have an alkane with 4 carbons. We can kind of name it after that butyric acid. Well, where did butyric acid's name come from? Well, that's easy. The person who discovered it. They were able to find butyric acid in the place where we most find butyric acid, and that's in rotting butter. So, the butyr comes from butter, and the acid of butter is butyric acid. Butyric acid has 4 carbons, butane has 4 carbons. Okay. Now, propane, ethane, methane, I'll leave that research up to you guys, okay? You just, frankly, have to memorize those. 1 carbon compound has the prefix meth, 2 carbon compound, eth, 3 carbon, prop, 4 carbon, bute. And the good news for you, which I'm sure will be greatly welcomed, is that everyone after that uses a more standardized system. For instance, 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5, is pentane. Okay, what if I have 6 carbons? Okay, we have hexane, then we have heptane, octane, nonane, decane. Now, of course, if you want to really impress me, you'll learn then undecane and dodecane. Etc., etc. I don't expect anybody to know past 10. Okay, 10's as high as I will expect. Okay, so those at least make a bit more sense. Which brings us back to our example where we were discussing all the different isomers of pentane. Okay, these all have 5 carbons. These all have the exact same molecular formula. But can they all possibly have the same name? And the answer is no. We have to have a way of giving each one of those isomers a unique name. And basically what happened was, about 100 years ago, a whole bunch of chemists got together at a pub, and around 3 o'clock in the morning, one of them hollered out, "Hey, I got an idea. I have something that's going to screw with undergraduates for the next century. We're going to create a naming system for organic chemistry." Okay. The naming system is consistent, but boy, folks, there's some weird stuff in there. Okay. Some of the stuff that we're going to talk about, they probably came up with at 5 o'clock in the morning because it's just way out there. Luckily for you, though, for this part of the course, we're just going to look at some of the simpler naming conventions. The system is called IUPAC. Okay, and nobody is responsible for knowing what that acronym stands for. Just know that it's an internationally recognized organization. In IUPAC, what we do is we have a system of steps that we follow in deriving a name for an organic compound. Okay. The first thing we do is we need to identify any functional groups. Okay, right now that's easy. There are no functional groups. Which makes this what kind of a compound? They're all alkanes, right? Nothing special. No chlorines, no bromines, no aldehydes, no amides. Okay, the next thing we do is identify the longest chain of carbons. Okay. Now, for the alkanes that I've shown you thus far, methane, ethane, propane, butane, hexane, heptane, all those guys, it's kind of easy, right? You just count the carbons. But what if we have a case where there's branching? So I'm just going to put an example on the screen here that we can kind of follow through and submit it to the testing procedures that are required by IUPAC. Okay, how many carbons do we have here? 5. All right. So this is one of those isomers that we saw of C5H12, right? Okay. Now, when those carbons were all arranged in a straight line, what did we call that? Straight chain. It was called pentane. Okay. But here, what we're doing with IUPAC is we're identifying the longest continuous chain of carbons. Okay, and in this case, this is our longest continuous chain, okay, which is 1, 2, 3, 4 carbons long. Okay, once we've identified the longest chain, okay, the next thing we do is we number that chain. Okay, we number the chain starting from the most substituted side. Okay, so in this case, should we number from the left or from the right? From the left. 1, 2, 3, and 4. Now I know what some of you are thinking. Well, how did I choose to start at carbon 1 on that particular carbon? I mean, couldn't this have been carbon 1 here? Could I have counted through there? Yeah. They're the same. It's equivalent. All right. Okay, the next thing we're going to do is identify and name the groups attached to the chain. Okay, what that means, oh yes?
I don't understand what you mean by substituted.
Let me change that word, or amplify that word with branched. Okay, in other words, you're going to start counting from the end where the first branching appears. Okay? Okay, so what we do is we look at our parent chain here, and this parent chain has 4 carbons. Attached to that parent chain is this CH3. Okay. The CH3 is 1 carbon. Okay, so what prefix would we use to describe that? Okay, well, it would be based on methane. Okay, but we would call it a methyl group. Okay, we can also have ethyl groups, propyl, butyl. Okay, and basically the way that they are derived is by taking the prefix with ane at the end, and then we subtract out, well, sorry, that got a little crowded there. I'll do it like this. For the methyl, I'll do it like this. Methane minus the ane doesn't like that side of the screen. Methane minus ane plus a YL gives us methyl. Okay, and you'll see that same pattern following through with all the other possible alkyl groups. Where did I get that word alkyl from? Alkane minus ANE plus YL. All right. The next thing we need to do is start putting together the name. Okay, we look at the functional groups. In this case, there's no functional groups. That means the suffix we're going to use is going to be ane. We look at the longest carbon chain, which is 4 carbons long, and we figure out what does that correspond to. Is that meth, eth, prop, bute, pent? What is it? Bute. Okay, so this is actually based on butane. Okay, and there's a methyl group attached to it. So we would call this methyl butane. Now, in this particular case, this is kind of redundant, but I'm going to do it anyway. I need to indicate which carbon that methyl group is on. Now, in this particular case, it doesn't matter because if it were on the first carbon, well, then we'd have a problem because that makes this actually pentane. If that methyl group were on the third carbon, well, it's just a flip of having it on the second carbon. So, in this case, we don't really need to do this, but we're going to, just as an exercise, we're going to say that that methyl group is on the 2 carbon by saying 2-methyl butane. All right, so what I'd like for you guys to do is take about a 10-minute break, and when you get back, I got tons of practice problems for you to start working on.